Hey everyone, hello and welcome back to my channel, Your Physics Meet. Today's video is on central force motion, and in this video I have tried to cover the whole central force more or less. I have tried to make one compact video on this topic, so I think you will find today's video helpful. Here I have given the definition, examples and all about the central force motion, the characteristics of the motion, and each and every characteristics have been discussed in today's video elaborately. That's why the video has become a little bit longer. So if you have time in your hand, only then watch the video, okay? Because you need to keep some time for the video, and please don't skip the video and watch the video till the end, because all the informations are very much important to understand this central force motion, okay? And if you like this video, please give it a like and share this video with your friends, and please subscribe to my channel if you like it. And if you have any queries regarding this video, you can write it in the comment section below. I'm ensuring you that I will answer each of your questions, okay? So yeah, without a further delay, let's get started. Hello everyone, welcome to my channel, Your Physics Meet. You can see from the introduction that today we will discuss about the topic motion under central forces. What is a central force, how it acts, and what are the characteristics? We will discuss in today's video, and each characteristics are to be proved in this video. And if you have any kind of queries regarding this, you can write it in the comment section below. I'm ensuring you that I will reply all of your queries, okay? So first of all, what is the central force? Central force is a force which at every point of its field is directed either towards or away from a fixed point. And that fixed point is basically the center of force in the field, and its magnitude at a point is a function of the distance r only of the point from the fixed origin. What is r? R is basically the distance of a point. Suppose this one is the definition, right? The definition says that the central force is a force which at every point of its field is directed either towards or away from a fixed point. So what is the fixed point? You can see two pictures here, this one and this one. In the first picture, this is basically the center of force. Suppose we are giving it a name O. And in the second picture, this one is a center of force. We are also giving this a name O. In the first picture, the point particle P is moving such a way, you can see the direction of its movement. It's moving such a way that the force is acting along the line joining O and P along a direction this way, right? That is towards a fixed point. The fixed point is O, and the force is acting towards the fixed point, right? In this direction. That is towards the fixed point. And in the second scenario, that is the second picture, the force F is acting away from a fixed point. Why away? Because this force is acting this way, in this way. This is not acting in a way which is towards the origin. No, this is acting away from the origin. That is, in the first scenario, this one is a force which is an attractive force, because this O is attracting this point particle P along this direction. But in case of the second picture, the point particle P is not attracted, rather it is repulsive. This force is repulsive in nature, because this force is acting along the line joining O and P, but in this direction, that is away from that fixed point. So this one is a repulsive force. In the first case or the first scenario, the force F is a central force. the second force is also a central force. These two kind of forces, that is, if there is a point along which the force is acting either towards or away from that point, that is called the center of force. That is, this O is called the center of force, and the magnitude at a point is a function of the distance r only. That is, this force, this F is a function of r only. This force depends only on r. That's why I have written here F vector r as a function of r is equal to F as a function of r cap. That is, this force is only dependent on r. What is r? R is basically the distance between the center of force, that is O, and the particle for which this force is acting on, that is OP, is basically the r vector, that is the position vector of the particle from the fixed point or from the center of force. Okay, so this force or the central force is basically a force which only depends on the position vector or the distance r, and the direction of the force is always acting away from or towards a fixed point. That is, it is acting along this line, either in this direction or in this direction, right? That is, either it is acting along this direction, that is towards O, or away from O, but does not matter towards or away from, it is always acting along r, that is the distance vector or the position vector, right? That is, it is always acting along the line joining O and P. That's why the direction vector is always r cap, right? It may be plus, it may be minus depending on the direction. If the direction is towards O, that is, if the direction is along this direction, it is a negative sign because it is acting towards a fixed point. And if the force is along this direction, that is away from a fixed point in this direction, this force should be positive in nature. So depending on the force is negative or positive, it is given as attractive or repulsive. Okay, so in first case, if the force, if is a function of r, and if it is less than 0, that is, if the force is negative, this force is always attractive. Which one is this one is always attractive. And what is the example? The first one. The first one is the example of attractive force. Why? Because in this scenario or in this case, the force is acting towards the direction of O. Okay, and so that's why it is negative, but always the direction is always along the line joining O and P. That is why we are writing here r cap. R cap is the unit vector along the line joining O and P. Okay. In the second scenario, the force F is a function of r that is greater than 0. Why greater than 0? Because the direction is away from a fixed point, that is along this direction, and this one is positive. If the force is in this direction, that is along the negative direction towards origin, that is negative. But if it is away from our origin, it is along a positive direction. If it is towards origin, it is along a negative direction. So this one is a positive force, this one is a negative force. So if the force is positive in nature, that is, if the force is greater than 0, it is always a repulsive force, right? So we can see here two kind of forces. One is attractive and other is repulsive. If the force is attractive in nature, then the motion becomes bounded because it bounds the particle in a particular trajectory. Okay, so the first case, the bounded motion, the central force motion is basically divided into two parts. One type of motion is called bounded motion and the other type of motion is called unbounded motion. So the first scenario where the force is attractive in nature, that is, the particle is attracted towards a fixed point, That means this fixed point or the center of force always try to attract that particle or make that particle bound in a particular trajectory. That's why this always gives a bounded motion. It gives result to a bounded motion. But in the second scenario where the force is repulsive in nature, that is the origin or the O is always just repulsive in repulsive nature, that is it always rejects that one and it's try to repulse it, that is away from that fixed point. That's why this kind of motion is not bounded, because it is not just holding this, it is always just rejecting it, repulsive in nature. That's why this kind of trajectory or this kind of motion is unbounded in nature. So what are the examples of this kind of motions? In case of bounded motion, we can see in planetary motions, suppose the planets of our solar system, the trajectory of the planets of our solar system is an example of bounded motion. And the example of unbounded motion, we can say the alpha ray scattering experiment. That is Rutherford's alpha ray scattering experiment is an example of the unbounded motion. Okay, so these two are the examples. The first one for bounded motion, we can give the example as the planets of the solar system or the planetary motion of the planets of the solar system are the example of bounded motions. And for the unbounded motions, the example is the Rutherford's alpha ray scattering experiment. Okay. Now come to the characteristics of motion under central force. So now we are going to discuss some characteristics of this central force motion. Basically, there are 4 characteristics and we will prove each of the characteristics. Okay, so this video is becoming a little bit long, but please don't skip the video and try to watch the video till the end. Okay, and afterwards, if you have any kind of queries, you can write that in the comment section below. I will ensure you that I will definitely answer each and every question. Okay, now the first one or the first characteristics, that is number 1, the angular momentum of the particle is a constant of motion. Now, what is angular momentum and how it is written? So the angular momentum is basically L. It is written as L, or the symbol of angular momentum is given as L, right? So if the linear momentum is written in P, P is the linear momentum and L is called the angular momentum. They are basically the symbols, right? So what is the relation between the angular momentum and the linear momentum? L is always equal to R cross P, where P is the linear momentum, R is the position vector or the distance vector, which we already have mentioned before, and L is equal to the angular momentum. And these terms are very important in the rotational dynamics. Okay, so in place of P, P is the linear momentum. It can be written as m into v. So what is m, what is v? M is the mass of the particle and v is the velocity of the particle. So basically the motion in a particle supported or characterized with mass and velocity is the linear momentum, and r cross p is basically the angular momentum which is imparted in a particle which is basically rotating or in a rotational frame, right? If there is no rotation, there is no angular momentum, there is only linear momentum. That is, if the particle is here and now it is just translating along this line, there is only a velocity v, and if mass of the particle is m, then the linear momentum will be mv. But as the particle is just translationing, or particle is just in a translational motion along this line, so there is no rotation and not at all there is any angular momentum. But if the story of angular momentum comes if there is a rotation for the particle, or if the particle is rotating, that is, here this one is suppose a star, suppose this one is sun, and this one is earth. Suppose this one is sun, this one is earth, and earth is just rotating. This one is in a focus actually. Sun is in a focus of the Earth's trajectory. It is an elliptical orbit. So basically Earth is rotating along Sun, making or just placing the Sun in one of its foci, right, or one of its focus. So L is basically the angular momentum. Why I am writing this? Because this particle, suppose here E is the Earth, and Earth is moving in a planetary motion, or it is showing a central force motion. So as it is rotating, right, it is rotating in this direction. As it is rotating, so here comes the story of angular momentum. If it does not rotate in this way, if Earth was just translating along a line, then there would be only m and v, there would not be this term L, right? So if the particle is rotating, only in that scenario there would be the term angular momentum. Anyways, so the first point is the angular momentum of the particle is a constant of motion, right? So how can we write it? How can we prove this one, right? So angular momentum is constant of motion in case of central force motion. First of all, for central force, we always can write this force, this central force Fr is always equal to Fr, that is the magnitude of that force, into r cap. That is, this force is always a function of only this distance vector, that is r. R is the distance between the center of force, that is O, which we already have mentioned here. This is O and this is P. So the distance between O and P is basically r, that is the distance vector. Now F is a function of r and it is always acting along the line joining them, that is r cap, right? Either this way, either direct towards or away from, does not matter. It always acts on the line joining them, that is the vector, the unit vector is always r cap. Okay, now if we have to prove the angular momentum of the particle is a constant of motion, if we need to prove it, how can we prove it? Now the momentum, angular momentum is constant of motion. If any of the term or any of the parameter is constant of motion, it means it does not change with time, right? Or it is constant, it does not vary with time. That is, if L is the linear angular momentum and we make a derivative of L with respect to time, that is t, dl by dt, and if we can show dl by dt is equal to 0, that means L or the angular momentum does not vary with time. That is, the angular momentum is particularly a constant of motion. So we just need to prove it, that is dl by dt is 0, and if you can prove this one, then this number 1 point is proved, that is the angular momentum of the particle is constant of motion. We just need to prove it. How can we prove it? First of all, we all know that torque, tau, suppose I am writing it as tau, torque or tau. What is torque? Basically the force acting on a particle in case of rotational motion, right? How is the torque related to force? Tau is always equal to r cross F, right? Where F is the force acting along the translational motion and tau is the torque acting, the force basically acting in rotational motion is called torque. So the relation between force and torque is tau is equal to r cross F. Now we also know that tau is equal to dl by dt. That is, the change of linear momentum with respect to time gives the amount of torque needed. In same way, the force F is equal to dp by dt. We also know that. That is, the change in linear momentum with respect to time gives the amount of force. The change in angular momentum with respect to time gives the amount of torque. Anyways, this equation is not needed here. We just need this one equation. Tau is equal to dl by dt. Now, how can we prove it? Now, if we can show that torque is equal to 0 in this scenario, that is, if we can show torque is 0, that means dl by dt is equal to 0. And if dl by dt is equal to 0, that means L is constant of motion. We just need to prove it, right? Now, just check it out, what is the amount of torque in this case. Okay, so we already have written that tau is equal to r cross f. Here f is a function of r, right? So f as a function of r, we can write it here. So from here we can write tau is equal to, in case of r, we can write it r cap, where this one is the magnitude of r into r cap cross f r magnitude of f r cap, right? So this one is cap. So from here we can write r cap cross r cap. Any unit vector having a cross product with itself always gives a 0. That means r cap cross r cap is a 0. This one, r cap cross r cap is a 0. So tau is equal to 0. So if tau is equal to 0, that means tau is equal to dl by dt. That is, dl by dt is equal to 0, right? That means L is equal to constant of motion, and we need to prove it right here, from here, right? So the angular momentum of the particle is a constant of motion, and we could prove it from here. L is a constant of motion, or torque is equal to 0. So the first scenario, or the first characteristics of the motion under central force is proved. Now go to the second one. The motion is planar, that is, the particle moves being always confined to a fixed plane. From here we can write that the angular momentum L is equal to r cross p, and from the first one, L is a constant of motion, right? L is a constant of motion, that is, the magnitude and the direction of L is constant. This one is constant. And if the cross product of r and p gives the value of L, that is, L always resides on a plane which is perpendicular to the plane containing r and p. Suppose I am just showing here 3 axes, okay, x, y, z axis. Now if this one is r axis, this one is p axis, suppose, that means L becomes this one, that is, L is always along the line which is perpendicular to the plane having these 2 vectors, r and p vectors, right? So if this one is the plane containing r and p, L becomes this vector, right? Again, if we are writing, suppose this is the plane, so this is x, this is y, this is z. Suppose this xz plane, suppose r and p resides in this plane, okay. Suppose this one is r and this one is p. So r and p resides in this plane. So L resides in the perpendicular plane of this, that is along y direction. Always it means that cross product always gives the vector, or the cross product of 2 vectors always gives a vector which resides on a plane perpendicular to that mother vectors, right? So this L always resides on a plane which is perpendicular to the plane containing these 2 vectors r and p. As L is constant, that is, the direction and the magnitude of this vector L is constant, that means this plane is also constant, because if the perpendicular is constant, that means this plane becomes a constant. If L is along this direction, then r and p should be along this direction. If L is along this direction, then r and p should be along this direction. That is, if the value of L becomes constant, then the two vectors r and p should be along the plane containing r and p should be perpendicular to the line L, right? That means this should be a planar motion, that is r and p always should reside in one plane, and that plane should be perpendicular to this one axis or to the L axis, or L should be perpendicular to that plane containing these two vectors r and p. So this particle is moving in a plane having a r and p in a particular plane, that is the movement of the particle is planar or the motion is planar. Okay, that means if L is constant, that means the direction and the magnitude of the angular momentum is constant. That means r cross p becomes constant because L is constant, that is r cos p is equal to constant. That means r and p resides in a particular plane, and which plane? The plane containing r and p should be fixed, which should be perpendicular to this angular momentum vector. Okay. Suppose again I am writing a particular picture. Suppose this is x, this is y, this is z. First of all, if this one is the direction of L vector, that means r cross p should be perpendicular to this, or the L vector should be perpendicular to r cross p vector, that is r cross p vector should lie in this plane, right? As L is the perpendicular along this plane, right? So what is the r and p vector here? Suppose this one is the r vector and this one is the p vector, and they both lie on a particular plane which is perpendicular to L. Okay, so the particle always is confined to a fixed plane, right? So here the particle is confined in xy plane. If L is along x axis, then r cross p should lie in which plane? Right, in yz plane, along this way, right? If L is along y direction, suppose this one is the direction of L, then in which plane the r and p should reside? If L is along y axis, r and p should reside in right xz plane. Okay, so it becomes that if the motion is, in case of planetary motion, in case of central force motion, if the motion is planar, that is the particle moves always in a fixed plane. Why it is possible? Because L is constant, and L is constant has already been proven in the first scenario. Okay, so the 2 points have been proved. Now we are coming to the third one, that is the areal velocity of the radius vector. What is the radius vector? That is the line joining the particle with the center is constant. Suppose we are drawing a picture here. Suppose this one is the line joining the particle with the center. This one is the center O. This one is a particle P. Okay. Now the line joining O to P, this is basically the radius vector. We are giving it a name R vector, radius vector. Okay. And the particle, suppose P is going along this direction. Suppose this one is the trajectory of the particle. The P is moving along this direction. Okay. So P is moving along this direction. Suppose after a particular time dt, the particle comes here. Okay. Now the position vector is here. Suppose this is R, new R. We are giving it a name R prime. Okay. Now the distance it covered in time dt. Suppose in time, in the first scenario, when the particle, we are just taking the time is equal to 0, this one is P, and after a time dt, it comes to a place, this one, this is a point P prime. Okay, so from P to P prime, the distance is dr, and the particle covering this distance dr in a time dt. Okay, now the area under the two distances. That is basically the radius vector covers an area, this area covers this area in a time dt. So this one means basically a areal velocity. Areal velocity is nothing but the area swipes out by a particular vector per unit time is called areal velocity. The distance covered per unit time is called the velocity, and the area covered or swipes out by a vector, by a radius vector per unit time is called the areal velocity. Okay, suppose this radius vector r, this one is the radius vector r, and this is covering this whole area in a time dt, right? This r vector covers or swipes out this area, right, in a time dt. So if the amount of area is dA and it is covering, or this radius vector is swiping out or covering this area in time dt, then per unit time the amount of area the r vector swipes out is dA by dt, right? If dA amount of area is covered in time dt, then if dA amount of area is covered in time dt, then in unit time the area is covered is equal to dA by dt, right? So this dA by dt is equal to the areal velocity, right? So what is areal velocity? Areal velocity is the area covered by the radius vector per unit time. Okay, and we need to prove that this one is a constant. Okay, so how can we prove it? Suppose this dA, what is the amount of A, right? What is the amount of this area? We need to find the amount of this area. So this looks like quite like a triangle, and in this case this dr is very small and it is nearly equal to a straight line. That's why this OP P prime is looking like a triangle, and the area of this triangle A is equal to half cross R cross dr, right? As OP P prime is looking like a triangle apparently, as dr is very small and is nearly equal to a straight line, that's why the area swipes out by this radius vector r in time dt is equal to A should be equal to half cross R cross dr, right? Dr is the distance between P prime, okay, and R is the distance between OP. OP is equal to R and P prime is equal to dr, okay. So half R cross dr should be the value of A. Now we need to prove the amount of areal velocity is constant. That is ddt of half cross R cross dr should be a constant. Now how can we prove it? R vector by 2, suppose into, we can write it dr by dt, okay, R by 2 into dr by dt. So what is dr by dt? They are basically, this cross does not mean it is a cross product. This one is just an into, right? This one is r into r, that's all. So r by 2 into dr by dt. We are just putting here why r is, we are not taking the derivative of r, we are just putting this dt with respect to this dr only, or we are just making the derivative of this dr. We are not giving this dt in lower of r. Why? Because r is not a variable quantity here. R is this vector, this is the radius vector, which is variable here, this dr, because if we are putting a time t excess, that is if dt becomes a little increases, dt if increases a little bit, dr will also increase a little bit, that is dr is dependent on dt. That's why we are giving dr by dt. That is, we are just making a derivative of dr with respect to dt. Okay. Now, suppose r by 2 cross dr by dt, we are taking a m here and we are putting it a m here also. So, we are just multiplying this by m in denominator and the numerator. That's why we are coming with a equation r by twice m into ddt of m dr by dt. Now, what is dr by dt? Dr by dt is v, that is m into v, right? Because m does not depend on t. So, we can take this m outside of this derivative and now it becomes m into dr by dt, right? So, we can just take this m outside of this derivative. So, m into dr by dt, and dr by dt is equal to v. So, m into v. Now, m into v is equal to p, that is linear momentum. So, r by twice m into mv is equal to p, that is linear momentum. Now, what is r cross p? Here we already have written r cross p is equal to L, that is the angular momentum, right? So, here we can write r cross p is equal to L, angular momentum, by twice m. Now, in case of central force motion, we already have proved that the angular momentum of a particle is constant of motion, that is L is equal to constant. Now, from here L is constant. Okay, 2 is a constant quantity and m is the mass of the particle, which is also constant. So, this total part L by twice m becomes constant. And what is L by twice m? It is actually dA by dt, that is the areal velocity. So, it becomes that the areal velocity is also constant. So, we need to prove it that the areal velocity of the radius vector is constant, and we could prove it here. Okay. So, the first part was the angular momentum should be constant. The second part was the motion should be planar, and the third part became that the areal velocity should be constant. So, we could prove the three parts, and now this is the last part, that is the central force is conservative in nature. Okay, so how can we prove that? Now, the central force F is a function of r, and it can be written as F r cap, right? We are just giving, we can write it here like a magnitude F r, or I can write it as this way, or if I am writing F r, it becomes a magnitude. I am just giving this one a magnitude. So, instead of giving the mod here, I am just writing it is this way. This one is the magnitude part and this one is the unit vector part. Now, this r vector can be written as F r into r vector should be written as r by mod r, right? This one is also a mod. I am giving it a mod. Okay. Now, what is this? F r into r vector by r cap, or this one is the mod of r. So, what is the r or the mod of r? I am writing here this way, F r vector by r. Okay. So, r is the magnitude, F r is also the magnitude. I am not giving the mod to make it a little bit easier to see. Okay. So, F r into r vector by mod r, actually this r is equal to root over of x square plus y square plus z square, right? Why so? Because actually r is equal to, r vector is equal to I cap x plus j cap y plus k cap z, right? The r vector or the distance vector or the position vector is always written in this form in Cartesian coordinate system, that is I cap x plus j cap y plus k cap z, where I cap, j cap, k cap are the unit vectors along x axis, y axis and z axis respectively. Okay, so from here the mod of r or r is equal to root over of x square plus y square plus z square. So I am just writing it here. Now we have to prove that the central force is conservative in nature. And how can we prove any vector is conservative? We can prove it by making a curl of that vector. And if the curl of that vector becomes 0, then we can prove that the vector is conservative in nature, right? Okay, so if we need to prove that the central force is conservative in nature, so we have to prove del cross F, that is curl of F. Del cross operation is called a curl operation. So the curl of F should be 0, or the curl of central force should be 0. If it is 0, then we can make sure that this force is conservative in nature. Okay. Now, what is the del operator? Basically, the del operators looks like I cap del x plus j cap del y plus k cap del z, right? Now, del cross F. So, if we are taking this del cross F in a matrix format, we can write it like, and what is F? We are writing the value of F here. F is equal to I cap, if we already have written it here, right? F is equal to Fr into R vector by R, right? This one, Fr is equal to R vector by R. So we can write it from here. F is equal to, F vector is equal to F as a function of R into R vector by R, right? Now, R vector can be written as, from here, R can be written as I cap x into j cap y into k cap z. So, from here, Fr by R into, in case of R, in place of R, we can write I cap x plus j cap y plus k cap z, right? So, if we write F vector is equal to, from here we can write I cap Fr by R x plus j cap into Fr by R into y plus k cap into Fr by R into z. Okay. Now again we can write F is equal to Fx I cap plus Fy j cap plus Fz k cap, where Fx, Fy, Fz are the components of the force along x direction, y direction and z direction respectively. So Fx is basically this one. So Fx is basically equal to this part, Fy is basically equal to this part, and Fz is basically equal to this part. So to make it a little bit easier for the equation, we are writing Fx, Fy, Fz. Okay, now we need to prove that del cross F should be equal to 0. So if we are writing this in a matrix format, del cross F, right? Del cross F, and we need to prove it as 0. So what is del cross F? Del is I cap del x plus j cap del y plus k cap del z. We already have written it before. So from here we can write del cross F equal to, in matrix format, I cap j cap k cap. For del it is del x del y del z, and for F I am writing this from this equation, Fx, Fy and Fz. So what is Fx, what is Fy, what is Fz? We already have written here. Fx is this part, Fy is this part and Fz is this part. Okay. Now suppose from here we will have three components. One part will be for I cap, the second part will be for j cap, and the third part will be for k cap. Okay, well, I'm writing it. Suppose for the part I cap, or the coefficient of I cap should be equal to del Fz by del y minus del Fy by del z minus j cap. J cap into this, that means del Fz by del x minus del Fx by del z. Okay. And for the last part k cap, it becomes For the last part k cap, it becomes del fy by del x minus del fx by del y. Okay, now we have to prove del cross f should be equal to 0. That is, if the values of this coefficients are 0, then it gives del cross f should also be equal to 0. Suppose we are taking the first coefficient, that is the coefficient of I cap. What is the coefficient of I cap? Del fz by del y minus del fy by del z, right? So del y of fz, what is fz? From here fz is this one. So from here fz is this one, fr by r vector into z. So here del fz by del y we are writing del fz by del y, that is, it becomes from here fz is equal to fr by r vector into z. So del y of fr by r vector into z. So del y of all this we can write here del r of this into del r by del y, right? Now from here z does not depend on r, so we can put it outside. Now del r of fr by r vector. So what is fr by r vector? R is basically root over of, and for this del fr by r, del r, oh, we are just, wait. So del r of fr by r, we are not just minimizing it, we are just putting it as it is. Now del r by del y, what is r vector? Basically what is r? R is equal to, we already mentioned before, x square plus y square plus z square root over, that is r. So del r by del y, what is del r by del y? From here we can write this one is, this is whole to the power half, right? From here we can write this whole to the power half. That means from here it is a 2 and this portion comes downward, that is x square plus y square plus z square, and in the upper portion we will have del r by del y, that is 2y. So from here it becomes y by root over of this, that is r, right? So del r by del y is equal to this one. This is nothing but a derivative. We are just derivating this r with respect to y, and if we make a derivative of this one, it becomes a y by r. Okay, so from here we can write the value of del fz by del y equal to z into, sorry, this one, del r by del y. In place of del r by del y, you can write a y by r. So from here we can write zy by r into del r of fr by r vector. So this one is the equation 1. Okay. Now for the second scenario or the second portion, that is del f by del z, del fy by del z. Now what is del fy by del z? From here del fy by del z is equal to, what is fy? Fy is equal to this one, that is fr by r vector into y. So from here del z of fr by r vector into y, the derivative of this with respect to z. So we can write here del r of this into del r by del z, similarly as before. And now del r by del z, what is del r by del z? Again r vector is basically equal to root over of x square plus y square plus z square. So del r by del z is equal to, it becomes a 2 downwards and root over of x square plus y square plus z square, and the del r by del z, that means 2z. So z by this one, so del z by root over of this is equal to r, so this z by r. So del r by del z equal to z by r. So in place of here we can write del r of f r by r. Y does not depend on r, so we can put this outside. So y into this one into del r by del z. In place of del r by del z we can write z by r. So here it is z by r. So it is equal to yz by r into del r of f r by r. Okay, now if this is equation number 2. Now from equation number 1 and equation number 2 we can see that the coefficient of x vector or the coefficient of I cap for the curl of f. For the curl of f we are just expressing these two values, right? This one and this one. We just find the values of these two coordinates or these two values to just calculate the coefficient of I cap, and the coefficient of I cap becomes this, that is del fy, this one. So that del fz by del y is equal to this one, zy by r, del r of this, and this del fy by del z is equal to del fy by del z is equal to this one, yz by r into del r of this. Now from the equation 1 and 2, from the equation, this one is 1 and this one is 2. From the equation 1 and 2 you can clearly see that these two values are exactly the same, right? This del fz by del y, so this equation del fz by del y, and thus this equation del fy by del z, the equation number 2, and this equation number 1 is basically exactly the same. It is equal to zy or yz by r, del r of fr by r. That is 1 and 2 are exactly the same. That's why this value del fz by del y minus del fy by del z cancels out, as these two values are exactly the same. So it becomes a 0. In the same way, you can calculate that the coefficient of j cap and the coefficient of k cap becomes also 0. That means this del cross f becomes a 0, and if the curl of any vector becomes 0, then that vector becomes a conservative vector. The curl of any vector, if it is 0, then that vector is also called an irrotational vector. Okay, so this is an irrotational vector. So this vector is an irrotational vector. Why? As the curl of this vector becomes a 0, and as this one is an irrotational vector, and as the curl of this vector becomes 0, this one becomes a conservative vector. Okay, so this way the central force, we just could prove that the central force is a conservative force in nature. Okay, so the number 4th category or the number 4th characteristics, that the central force is a conservative force, we could prove it. So these 4 are the basic characteristics. So again I am just telling it once more for you to recall this all. Number 1, that the angular momentum of the particle should be constant of motion. Number 2, the motion should be a planar motion. Number 3, the areal velocity of the radius vector should be constant. And number 4, that is the force or the central force should be conservative in nature. If these 4 categories are fulfilled by a force, only then that force should be called a central force. Okay, so this was all about today's video. I think you could be benefited by today's video, and if you like this video and if you like my way of teaching, then please support me and subscribe to my channel. And if you need more videos from me in any other topic, you can write it in the comment section below. And if you have any queries regarding this video, you can also write that in the comment section below. I will definitely give answer to all of your questions. So thank you and see you again in the next video.